Imagine you are 5 hours into Reduction Critical Refactor using a high-end AI coding assistant. You provide a loosely defined vibe-based prompt like update the authentication logic to support multi-tenant OIDC, and the AI proceeds to rewrite 40% of your core middleware. Initially, it looks impressive, but then the intent drift hits. The agent hallucinated a legacy library version, broke your React state synchronization, and introduced a race condition that wasn't there before. This is the hallmark of vibe coding, a deceptive speed at the start that leads directly into a refactoring hell where the cost of fixing AI mistakes exceeds the time saved. In the world of professional engineering, relying on LLM's mood or vibe is a technical debt factory. We are seeing experienced developers lose entire days trying to reverse engineer what an autonomous agent did to their codebase because there was no source of truth to bound the agent's behavior. This failure state isn't an AI problem. It is a methodology problem that will break every major project by 2026 if not addressed. By the end of this lecture, you will understand exactly how to move from this chaotic guessing game to a deterministic, spec-driven workflow. But first, let's look at how we transition from chatting with models to orchestrating high-precision agents. This transition starts with a fundamental shift in architecture. Currently, most developers are just vibe-checking their way through PRs, which is a recipe for disaster in enterprise-scale environments. We need a way to ensure that the AI's output is not just plausible, but correct by design. Currently, your AI is a junior dev without a senior's guidance, and that is about to change. Pay close attention to how we define the boundaries of intent. This is the only way to survive the coming wave of autonomous agents. What happens when we stop treating AI as a magic box and start treating it as a compiler? The answer lies in moving away from the prompt and towards the specification. Now, let's see what a predictable architecture actually looks like when driven by agents. Such a shift is not just an option. It is a necessity for anyone aiming for senior-level engineering in the AI era. Till you master this, you are just gambling with your codebase. There is a specific threshold where vibe coding stops working. Next, we will see the alternative. Payoff. Now that we have identified the nightmare of intent drift, let's look at the architectural patterns that allow for first-pass success without the chaos. To move beyond the chaos, we must adopt a framework of predictable architecture. In 2026, the hallmark of a senior agentic engineer won't be how well they write prompts, but how well they define the system of truth. This involves moving from a chat-centric model to an orchestration-centric model. In this new paradigm, we use structured specifications, think markdown files, protobufs, or JSON schemas that serve as the absolute constraints for the AI agent. Instead of saying make it look like this, we provide a rigorous definition of state, interfaces, and behavior. This ensures first-pass success, where the agent generates code that passes 95% of tests on the first attempt because it was bounded by a strict spec. We are moving toward a world where the spec is the source code, and the implementation is just a compiled artifact generated by the agent. If the spec is wrong, the code is wrong, but the feedback loop becomes incredibly fast. Experienced teams are already using tools like SpecKit or custom MCP servers to feed these constraints directly into the agent's context. This shift minimizes the human-in-the-loop burden and focuses human intelligence on high-level design and edge case discovery. If you continue to develop via simple chat interfaces, you are building on sand. The professional standard is shifting toward agents that can reason over a workspace, but only if they are given a map. Without a map, an agent is just a very fast way to make mistakes. We must learn to build these maps with precision. Is it possible to achieve this level of control with current tools? Absolutely, and it starts with understanding the move from vibe to structure. You might think this sounds like more work, but it actually eliminates the 40% time wasted on fixing AI hallucinations. But wait, why is this shift happening now, and who is leading the charge? Question: this method is becoming the industry standard, but who officially declared the death of vibe coding? Let's look at the expert warning that changed everything. Andrej Karpathy recently sent shockwaves through the dev community by declaring that the era of vibe coding, where we just throw text at an LLM and hope for the best, is rapidly ending. He pointed out that as models become more capable, the bottleneck is no longer the model's intelligence, but the human's ability to specify the problem. This is where agentic engineering comes in. It's a move away from the copy-paste workflow toward a world where software is built by autonomous systems that follow a rigorous engineering loop: plan, execute, test, and correct. Karpathy's warning is clear. If you are still just chatting with an AI, you are not an engineer. You are a hobbyist. In professional 2026 environments, we expect agents to operate on entire codebases, meaning the prompt is actually a multi-layered set of instructions and constraints. We are seeing a shift where coding is being replaced by spec writing and reviewing. This isn't just about efficiency, it's about reliability. In the field, we see that agents, given a structured plan, have a significantly higher success rate in complex refactors than those relying on zero-shot prompts. This is the agentic loop. It requires us to think in terms of state machines and system boundaries rather than just syntax. If you want to remain relevant, you must master the art of directing these agentic workflows. The era of the prompt engineer was a short-lived transition. The era of the agentic systems engineer is the end game. But how did we get here so fast, and what does the data show about this massive market pivot? The evolution of our tools is a direct response to the failures of the past year. We have seen the limits of what a simple chat window can do. Teaser, this shift isn't just a trend, it's a fundamental change in the software development lifecycle. Let's look at the timeline of how we got to this SDD dominance. If we trace the evolution of AI in coding, the trajectory is undeniable. In 2023, we were amazed by simple autocomplete. In 2024, we shifted to chat-based assistants like Claude and ChatGPT, which popularized vibe coding. But by late 2025 and heading into 2026, the market is pivoting hard towards spec-driven development, SDD. Why? Because the scale wall. Vibe coding works for a single function or a small script, but it collapses under the weight of a 100,000-line enterprise repository. Major players like Anthropic are releasing features like Model Context Protocol (MCP) to allow agents to read the architecture of a whole system. Market data indicates that teams adopting SDD have a 3x higher maintenance efficiency than those using ad hoc AI tools. We are seeing the rise of spec-first tools like Kiro, Cursor's advanced agent modes, and Claude Code, which all demand more than just a vibe. They demand context, constraints, and clarity. This is the 2026 shift, treating the AI as an agent that executes a blueprint, rather than a psychic that guesses your intentions. If you don't adopt SDD, you'll find yourself stuck in a loop of fixing AI-generated bugs while your competitors are shipping features at agentic speed. The transition is happening now, and the tools are already in your hands, waiting for you to provide the right structure. The question is, are you ready to stop talking to your IDE and start engineering your agents? This change isn't just about the tools, it's about the very definition of a developer. But to truly master this, we first need to define what a spec actually looks like in this new world. Pay off now that you see where the industry is headed, it's time to get technical. In the next chapter, we'll move from what to how by formally defining spec-driven development, SDD, and its core components. In the early days of AI coding, we relied on vibe coding, just chatting with a model and hoping for the best. But in a 2026 production environment, hope is not a strategy. Vibe coding fails because natural language is inherently ambiguous, leading to what I call the ambiguity tax, where you spend more time fixing hallucinations than writing logic. Spec-driven development, or SDD, replaces these loose vibes with structured specifications. Think of it as a formal contract between the human architect and the AI agent. Instead of saying make a login page, you provide a version-controlled YAML or Markdown schema defines state transitions, error boundaries, and security constraints. This transition from chatting to specifying is the foundation of agentic engineering. When your requirements are versioned just like your code, you eliminate the drift that happens when an AI forgets a prompt from 10 minutes ago. But why exactly does the spec need be the primary artifact? Let's look at the hierarchy of truth in modern workflows. In the SDD paradigm, we treat code as a secondary, disposable byproduct. This is a massive mental shift for many veterans. Traditionally, the code was the truth, and documentation was just a courtesy. In 2026, the spec is the source of truth. When a bug is discovered, you don't go into the Python or TypeScript file to patch it manually. Instead, you update the specification, the blueprint, and the agentic engine regenerates the implementation. This ensures that the documentation and the execution never diverge. If you find yourself manually editing a line of generated code, you've already lost. You've introduced shadow logic that the agent won't understand in the next iteration. By keeping the spec as the primary artifact, we enable massive scale refactoring that was previously impossible. If the spec is updated to change a global authentication protocol, the agent can propagate that change across 50 microservices simultaneously without human intervention. This sounds efficient, but how do we actually ensure the agent followed the spec? That's where automated validation loops come in. Verification is the final pillar. In SDD, every requirement in the spec must be testable by agent. If you write a requirement that an AI can't verify through a test runner or a formal prover, it shouldn't be in the spec. We use an automated verification loop where the agent's output is immediately checked against the spec's constraints. This isn't just about passing unit tests. It's about semantic verification. Does the generated API endpoint strictly follow the rate-limiting schema defined in the spec? If the agent produces code that works but violates a security constraint in the spec, the CI/CD pipeline rejects it automatically. This prevents the "I fixed it but broke something else" syndrome that plagues manual coding. In the field, I see teams that skip this step and end up with a pile of AI-generated spaghetti that no one understands. To avoid this, you need a checklist for every spec you author. But to do this effectively, you need to know the specific tools that are dominating the landscape in 2026. Let's dive into the tool stack next. The tool landscape of 2026 has matured significantly beyond simple LLM wrappers. At the heart of the enterprise stack is the GitHub Spec Kit, which integrates directly into the Git workflow to version specs alongside code. Then we have Claude Code, the dominant agentic engine that specializes in high-fidelity spec adherence. For infrastructure, AWS Kiro has replaced manual Terraform for many, as it allows you to describe cloud intent, which then auto-provisions via agentic loops. And we can't ignore Google Antigravity, which provides the runtime environment where these specs are continuously monitored for drift. These aren't just toys, they are part of a unified spec-first stack. Using these tools, we move from writing code to orchestrating agents. The real magic happens when these tools talk to each other, where a change in GitHub Spec Kit triggers AWS Kiro to re-provision the database while Claude Code updates the DAO layer. But wait, how do these tools compare when it comes to enforcing strict architectural boundaries? Let's break down the table. Choosing the right tool depends on your organization's need for enforcement rigidity. For example, GitHub Spec-Kit is excellent for general software, but if you're in a highly regulated industry like fintech, you might lean towards tools that offer hard constraints. A hard constraint means the agent physically cannot commit code if the spec's security audit fails. In contrast, soft constraint tools might just flag a warning. In the field, I've seen projects collapse because they used a soft tool for a hard requirement, leading to security leaks. This table compares top contenders. Notice how Claude Code excels in context window management, which is critical when your spec grows to thousands of lines. Meanwhile, AWS Kiro's strength is in short traceability, knowing exactly why a specific S3 bucket exists based on the original intent. If your tool can't tell you why a piece of code exists, it's not a true SDD tool. But having the tools is only half the battle. You have to restructure your entire team's workflow to use them properly. So how are enterprise teams actually adopting this? They are moving away from the developer as a typist model to the developer as a spec operator. The workflow now revolves around the spec repository. In this mind map, we see the central role of the spec operator who balances three distinct areas: requirements architecture, agent prompt engineering, which is now just spec refinement, and automated governance. Large organizations are even creating spec libraries pre-validated, reusable requirement blocks that comply with company-wide security standards. If you need to build a new microservice, you don't start from scratch. You pull the enterprise auth spec and the standard logging spec. This creates a Lego block approach to engineering where the AI handles the tedious glue coding while you focus on the business logic. This is how you scale a project in 2026 without the headcount explosion we saw in the past. But how do we actually implement this workflow day to day? In the next chapter, we'll look at the step-by-step SDD workflow from the first line of the spec to the final verified deployment. In the world of 2026 agentic engineering, a specification isn't just a README file for humans. It is a structured instruction set for an LLM agent. If your spec is vague, your agent will fill the gaps with hallucinations. This is why we move away from loose natural language to structured formats like Markdown-based spec templates or JSON schema for API definitions. Look at this example. Instead of saying implement a login feature, we define the state transitions, the required validation schemas using Zod or Pydantic, and the exact error codes to return. We are essentially writing code for the agent that then writes the code for the machine. By utilizing specific prompt engineering techniques within the spec like chain of thought requirements or few-shot examples, we ensure the agent remains within the guardrails. This high-quality specification becomes the single source of truth, minimizing the drift that usually occurs when an agent interprets your vibes incorrectly. But how do we ensure the agent knows about our legacy spaghetti code while reading this shiny new spec? Teaser context injection is the bridge that connects your new plan to your existing mess. Let's look at that next. Even the best spec is useless if the agent doesn't understand your current architecture. This is where context injection comes in. In 2026, we use tools like Model Context Protocol, MCP, or specific .context files to feed the agent exactly what it needs. We don't just dump the whole codebase that leads to lost in the middle issues where the agent forgets the spec. Instead, we use a tiered approach. First, global context containing your tech stack and design patterns. Second, the feature context involving related modules. And finally, the task context, which is your SDD spec. By using tools like Kiro or Spec-Kit, we can automate this pipeline so the agent receives a curated knowledge graph of your project. This prevents the agent from reinventing the wheel or using deprecated APIs that are still lingering in your repo. It's about building a surgical strike team of information rather than a blunt instrument. However, if your initial requirement is still fuzzy, no amount of context will save you. Question: can you spot the difference between a vibe and a spec? Let's compare them side by side. Ambiguity is the silent killer of AI-assisted projects. When you tell an agent to make the UI better, you are vibe coding, and you will get inconsistent results every time. In SDD, we quantify every vibe. Instead of better, we say reduce CLS to under 0.1 or ensure CA 2.1 AA compliance. Look at contrast here. On one side, we have the typical Jira ticket that leads to developer frustration and agent hallucinations. On the other, the SDD version provides clear boundaries, success criteria, and explicit do-not lists. This structured approach allows the agent to behave like a senior engineer who knows the trade-offs, rather than a junior who just guesses. By reducing ambiguity, you move the complexity from the debugging phase to the design phase, which is significantly cheaper and faster. Now that the blueprint is solid, let's see how we actually trigger the agent to start building the house without us touching the keyboard. Payoff: the magic happens when the agent starts writing code that actually runs the first time. Agent orchestration is the phase where the spec comes to life. Instead of copy-pasting code from a chat window, we use autonomous agents that operate directly on the file system. Tools like Ader Claude Code or custom-built Agentic CLI wrappers read the spec and start a loop. The agent just writes a single file. It creates a feature branch, updates the schema, modifies the business logic, and even adjusts the tests. This is engineering, not just coding. The agent treats the specification as its source of truth, and if it encounters a contradiction, it's instructed to pause and ask for clarification rather than making a vibe-based guess. We are shifting from being writers to being conductors of these AI agents. If the agent finishes the code, is it actually correct? Question: most people stop here. And that's where the project breaks. How do we prove the agent's work is actually production ready? The most critical part of SDD is the verification gate. We don't trust agents, we verify them. An agentic workflow must include an automated feedback loop where the agent runs the test suite it just updated. If the tests fail, the agent analyzes the stack trace, fixes the code, and tries again. This is self-healing engineering. We use a spec test code cycle. The spec generates the tests, and the tests validate the code. This ensures that even if the LLM has a momentary lapse in logic, the deterministic nature of unit and integration tests will catch it. In 2026, we often use linter as a judge and test as a judge patterns to keep the agent in check. This loop continues until the verification gate passes 100%. Even if the agent passes all the tests, you still shouldn't trust it blindly with your production branch. Payoff, there is one final layer of defense that separates the pros from the amateurs, the human-in-the-loop strategy. Finally, we reach the merging strategy. No matter how advanced the AI, the human remains the senior reviewer. However, your job changes. You aren't looking for syntax errors, you are looking for architectural alignment. You review the PR by comparing the agent's output against the original spec. If the agent met the spec, but the code feels wrong, your spec was likely incomplete. This feedback loop improves your spec writing skills over time. We use a human-in-the-loop, ATTL, approval process where the agent presents its changes, the test results, and a summary of its logic. Once approved, the code is merged into the main line. This SDD workflow transforms you from a code monkey into a systems architect. Theory is fine, but in the next chapter, we'll look at the actual scars from the trenches. What happens when the agent hallucinates a whole new database schema. Teaser ready for some horror stories. Chapter 4 covers the brutal lessons from the real world. Let's start with a disaster. I recently observed a project where a team gave an agent a vague instruction: upgrade the authentication module to support OAuth 2. Because there was no formal specification, the agent entered a recursive hallucination loop. It modified the core library, broke the downstream logging service, and attempted to fix the resulting errors by creating even more nested dependencies. By the time the developers checked the Git diff, the agent had essentially rewritten 40% of the codebase into an unreadable mess. This is the dependency hell of vibe coding. Without a spec-driven approach, the agent doesn't know the boundaries of its sandbox. It assumes it has permission to fix everything it touches, leading to cross-module corruption. In professional environments, this isn't just a bug. It's a catastrophic loss of architectural integrity that takes days to revert. We must treat agents like high-speed drills. Without a guide rail, they will destroy the material they are meant to shape. But wait, it's not just the code that breaks your budget is also at risk, and the next scene will show you exactly how much vibes actually cost you. In engineering, efficiency isn't just a buzzword, it's a line item on your cloud bill. When you rely on vibe coding, you are essentially paying for trial and error at scale. In a field study of 2 teams, the vibe coding group averaged 7 retry loops per feature, with each loop consuming thousands of context tokens. The spec-driven group, however, spent 30 minutes drafting a spec AMD file and achieved first-pass success 85% of the time. Look at the numbers. Vibe coding often results in a 400% increase in token costs due to redundant context rescanning. Furthermore, the time wasted by senior engineers reviewing hallucinated code is a hidden cost that dwarfs the LLM API fees. By enforcing a spec-first workflow, you move the cognitive load from debugging the AI to designing the system. This transition ensures that your expensive human talent is managing architecture, not acting as a janitor for AI-generated garbage. Is this approach scalable for large, complex organizations? I'll show you exactly how a 50-person team navigated this transition in the next section. Transitioning a large engineering organization to agentic SDD is a marathon, not a sprint. In the first month, velocity often drops. Why? Because developers have to unlearn the habit of chatting with the AI and relearn the discipline of writing technical specifications. By month 3, however, the curve inflects. We see standardization taking hold. Instead of 50 different prompting styles, the team uses a unified markdown-based spec format. This allows for interchangeable agents. If one LLM model fails, the spec remains the same, and you can simply swap the agent. By the 6-month mark, team velocity typically doubles because the knowledge transfer between developers happens through the spec files, not through long, synchronous meetings. This is the information management perspective. Software is not just code, it is a structured flow of requirements. Now, you might wonder if senior engineers resist this rigid way of working. Actually, the reality is quite the opposite, as we will see in the final piece of this chapter. There is a common myth that AI will replace senior engineers. In an SDD culture, the opposite happens. Senior engineers become more valuable as architectural orchestrators. They find SDD deeply satisfying because it eliminates the lottery aspect of prompting. Instead of hoping the AI understands their vibe, they use their 50+ years of experience to define the constraints, edge cases, and data contracts that the agent must respect. From an information management perspective, this is the pinnacle of professional engineering, ensuring that the source of truth is explicitly codified. This shift reduces burnout because the mental energy spent on boilerplate and debugging is redirected toward high-level system design. We aren't just prompting, we are managing information systems that happen to use LLMs as the execution engine. Now that we've seen the battles won and lost in the trenches, it's time to formalize these lessons into a set of concrete rules. In the next chapter, we will dive into agentic engineering best practices to ensure your 2026 projects don't just survive, but lead the industry. In the world of spec-driven development, your specification isn't just a document. It is the source code for your AI agents. If your spec is messy, the generated code will be garbage. We call this GIGO, or garbage in, garbage out. In the field, I often see teams treat requirements NumD like a dumping ground for half-baked ideas. Don't do that. You need spec hygiene. This means every functional requirement must be atomic, meaning it covers one specific thing and it must be verifiable. If you provide a 50-page monolith spec, the LLM will lose context due to the lost in the middle phenomenon. Instead, use modular specs. Organize your project with a dedicated spec directory where each feature has its own markdown file. Version control these specs just like your Python or TypeScript code. If a change isn't in the spec, it doesn't exist in the PR. This level of rigor is what separates the 2026 professional from a hobbyist playing with Claude. But wait, how do you know when you've written too much detail? That's where things get tricky. Let's talk about where even experienced developers trip up. The most dangerous anti-pattern is spec drift. This happens when you get lazy, let an agent like Claude Code or Ader generate a quick fix, and you forget to sync that fix back to your specification. Suddenly, the AI thinks the world is state A, while your actual code is in state B. The next time you ask for a feature, the agent breaks everything because its mental model is outdated. Another common trap is overspecifying. This is when you try to tell the AI exactly how to write a loop or which library to use for a simple task. You're hiring a high-reasoning agent, not a mechanical keyboard. If you micromanage the implementation details, you lose the velocity gains that agentic engineering provides. Trust the agent's reasoning for the how, but be ruthless about the what. Comparing these anti-patterns reveals the bottleneck in 2026 isn't AI intelligence, but human clarity. But what happens when the spec is perfect, but the underlying system architecture is a disaster? By 2026, the coder as we knew it in the 2010s is effectively obsolete. If your primary value is knowing the syntax for a specific framework, you are competing with agents that have a million token context window and zero fatigue. Your new role is the system architect. You aren't building the individual bricks anymore. You are designing the blueprint, the load-bearing walls, and the foundation. This shift requires deep architectural thinking. You need to understand how components interact, how data flows between services, and how to define interfaces that agents cannot misinterpret. Instead of worrying about a missing semicolon, you'll be obsessing over idempotency in your APIs, the CAP theorem implications of your database choice, or the security boundary of your microservices. This transition is scary for many, but it is the ultimate level up for those who master it. It moves you from being a tactical worker to a strategic orchestrator of digital systems. But there's one skill even more fundamental than architecture that will define the top 1% of engineers in the AI era. This is where the perspective of an information management professional becomes vital. In the AI era, software engineering is, at its core, information management. You are managing the flow of intent from a messy human brain into a structured digital format that an agent can execute with precision. This requires formal skills in ontology, defining what things exist, and taxonomy, how they are related. If you cannot define the lifecycle of a request or the specific entities in your system, you cannot guide an agentic workflow. In 2026, the best engineers are those who can structure messy real-world problems into clean, logical frameworks. This isn't vibe coding. It's engineering the vibes into concrete, mathematical specs. Mastery of this discipline allows you to scale projects that would normally require a team of 10, all by yourself. We have covered the how and the why of the agentic shift. Now it's time to conclude this journey and look at your immediate action items to survive the year ahead. Transitioning from vibe coding to agentic engineering isn't just a mindset shift. It requires a tactical deployment plan. Start by identifying a microservice, pilot a low-risk internal tool or a standalone module where the logic is dense but the scope is contained. Step 1. Define your specification in Markdown or JSON schema, ensuring every functional requirement has a corresponding test case before a single line of code is generated. Step 2. Select your driver tool. Whether you are using Claude Code for its agentic capabilities or anti-gravity for spec sensing, ensure the tool reads the spec as the source of truth. Step 3. Measure the spec-to-code alignment ratio. If the agent deviates, don't fix the code, fix the spec. In the real world, this spec-first approach reduces the debugging loops by nearly 40% compared to raw prompting. We often see developers jump straight to the LLM when they are excited, but the discipline to write the spec first is what defines a 2026-ready engineer. Now, is this overhead truly worth it when we scale beyond a single developer? Let's analyze the actual ROI when moving to team-wide adoption. Let's summarize the tectonic shift we've discussed throughout this course. Vibe coding relies on the magic of LLMs, hoping the model understands our intent through loosely coupled prompts. It is fragile, non-deterministic, and collapses as system complexity increases, leading to what we call intent drift. On the other hand, agentic engineering treats the AI as an executor within a strictly defined sandbox. We've moved from chatting with an LLM to governing an agent. This means formalizing requirements, automating validation loops, and ensuring that specs are code. In 2026, the competitive edge won't belong to the person who can write the cleverest prompt, but to the information management professional who can architect the most robust specifications for an agent to fulfill. This transition ensures that even as LLM models change versions, say, from Claude 3.5 to 4.0, your system's logic remains intact, because the spec is the invariant. If you think this is just another trend, wait until you see the final takeaway that separates high-performing architects from simple prompt monkeys. As we close this lecture, remember that engineering has always been about control and predictability. The Vibe era was a brief honeymoon phase where we were amazed by what AI could do spontaneously. The honeymoon is over. To build the infrastructure of 2026 systems that are resilient, scalable, and maintainable, we must return to the rigor of software engineering enhanced by agentic automation. Don't fall for the AI magic trap. Instead, master the art of spec-driven development. Treat your specs with the same reverence you used to treat your source code. The role of the developer is evolving from a writer to an architect and reviewer. Start small, enforce your specs, and watch your productivity decouple from your typing speed and attach itself to your thinking depth. This marks the end of our journey on SDD and Vibe coding. The era of vibes is over. The era of precision engineering has just begun, and the next lecture series will dive deep into the specific architecture of multi-agent orchestration.